Hi, welcome to SVM soft margin classifier. When the data is non-linear, that means not linearly separable, then we cannot use the hard margin classifier to classify the data perfectly. And when the data is noisy, that time also we cannot use the hard margin classifier to classify the data. So in these cases we can go for soft margin SVM classifier, which is allowing few misclassifications but almost classifies data points. The generalization of maximal margin classifier using the soft margin is called support vector classifier. Here it can be done by adding the slack variables. So here the slack variable is represented using the operator psi. Here every data point is having its own slack variable, which is allowing the observations to fall on wrong class side of the margin, but it will be penalized by the cost parameter c. So this is allowing the misclassification. You look at this, the data point here 10, which is located here in the positive class. So this is the positive class. The bottom data points are negative class, so which is wrongly placed in the positive class. So this is one of the misclassified data point. So for this, the slack variable value is greater than 1. Actually look at that, this is the negative hyperplane, negative marginal hyperplane. So the distance projection to this hyperplane, negative marginal hyperplane, is this much magnitude. So this is slack variable value greater than 1. But you look at the, for this data point, the slack variable values equal to 0, the which is the data positioned in between the w transpose x plus b equal to 0. This is the hyperplane. This one is w transpose x plus b less than or equal to minus 1. Okay, so here this value, for this data point, the psi value is less than 1. So here the data point which is misclassified is available always in the wrong side. The So the new constraint can be written for the soft margin. Here actual constraint is in the hard margin classifier. Actual output multiplied with hypothesis w transpose x plus b equal to, here, always greater than 0, always greater than 0. But here we are rewriting the objective function, actual output and predicted output multiplication give you the greater than or equal to 1 minus slack variable value for that particular sample. So here the objective function allows the margins to be as wide as possible. The marginal distance will be maximizing as far as possible. So here the slack variables are to be small as possible, to be small for preventing the margins violations. So when you are rewriting the soft margin classifier objective function, minimizing the parameter, minimizing the objective function, that means minimizing the error with respect to w, b and slack variable value. Here this is the value we got in the hard margin classifier, but in the soft margin we are using the additional term, the parameter c and the slack variable value. This is the error. This is the summation of error for m number of samples, subject to the condition should be always greater than or equal to 1 minus the total error. So the total error is always greater than or equal to 0 for m number of samples. So here c is the penalty parameter, which is the hyperparameter. We can select mostly, which is selected between the 0 to 1, which is controlling the trade-off between wider margin and lower total error penalty. So which is increasing the when the c is increasing, which is forcing the objective function to find the smaller value for slack variable. That is the error. So when your penalty parameter is large, you will get the very low marginal distance. So here look at that, the data points are classified almost 100%, but when you are having the penalty parameter c, cost parameter c, so there is the possibility of getting misclassification, but your marginal distance width is more. So this is uh, somewhat better than this one, because in SVM, uh, which is allowing the few misclassifications. So this is the proof for varying the penalty parameter in soft margin SVM. So but sometime the soft margin SVM will not provide you the optimal solution. In that case, you can go for kernel based SVM. So when can we go for hard margin and soft margin? When the data is linearly separable, we can go for hard margin. Suppose if our data is not linearly separable, so here the data is available, here one data available, here on, so this is not linearly separable. We cannot linearly separate this data in this direction or in this direction. In both direction, it is not at all possible. So in this kind of situation, we cannot go for hard margin. Soft margin we can apply because it is allowing the few misclassifications. So sometimes the data is linearly separable, but the margin is so small, like in this case. So in that time also, there is possible of overfitting of the model because of outliers. So in this case also, should choose a larger margin by using the soft margin SVM to generalize the model for other data set, new data set. Thanks for watching.